Hello, this is Mike McGinn, your instructor for Net I-105. Today we're going to talk about Chapter 7, the transport layer. Thus far, we have discussed the lower three layers of the OSI model, or in this case, they're showing the TCP/IP model. We've talked about the network access layer, which includes the physical and network access layers of the OSI model. And we've talked about layer 3, which is where the IP addresses live and how devices communicate and data gets routed via IP packets. Today we're going to talk about the transport layer. The transport layer is really the layer where the magic happens, and from the standpoint of allowing our applications to communicate with distant hosts, whether those or servers, whether they be in the data center within your own building or a web server across the internet. So what the transport layer does is it actually tracks the individual conversations between applications that reside on different computers. What it does is it takes data and puts it into segments, which then are put into the appropriate packets so that they can be routed via IP to the appropriate destination, whether it be instant messaging, web pages, of which there could be multiple, other IP devices, etc. So the transport layer ensures that even with multiple applications running on a device, all applications receive the correct data. So what we're going to get into here is we're going to talk about how that actually happens. So the graphic on 7114 does a nice job of kind of illustrating what actually happens. We have various applications that we run on our computers or servers, etc., and these are at the top layer. And the data is basically packaged into segments in the transport layer, and the transport layer utilizes a couple of protocols, either TCP or UDP. And then those segments, UDP segments or TCP segments, are encapsulated into IP packets, which then end up in frames and put on the wire, etc. So our discussion proceeds to talking about one of the specific transport layer protocols, which is TCP. TCP has three basic operations. They track transmitted data segments. They acknowledge that the data sent was actually received, and it retransmits any unacknowledged data. So the takeaway from this is that TCP is a connection-oriented protocol. It's important in a TCP connection that all data that is sent is received, and that all received data is acknowledged, and the message is sent back to the sending host so that it can ensure that there's no disruption or corruption of data. So I'm going to go ahead and play this video here so you can see what actually happens. I'm not sure how this will come across in GoToMeeting, but what it does is it transmits a group of segments, and then the receiving host then acknowledges that the first three segments have been received. It sends it back to the host, and then once it gets that acknowledgement, it sends three more. And if no segments get there, and an acknowledgement isn't sent, and based on a timeout, a client will resubmit those three segments until it ultimately gets its acknowledgement. So the advantages of TCP are obviously a highly reliable data communications between two hosts. Uh, Now, the consequence of that is because there's acknowledgments going back and forth and et cetera, it does provide a higher overhead on the network. And especially if the network isn't extremely reliable, there could be a lot of resends and such that have to go on. So that's just something to keep in mind as we begin our next discussion, which is UDP. Now, UDP is a lot like IP in that it is a connectionless protocol. It does not care whether or not the receiver gets the data. It just basically just sends it out and it's done with it. There are certain applications where this is suited for, where guaranteed receipt of data is not necessarily a showstopper. An example would be voice data. You lose one packet of voice data, it's not going to have uh, um, any impact of significance on the quality of the phone call. Another would be streaming video, etc. So what UDP does is it just basically sends the packets out and they go to the host and we're done. And then it goes and sends the next group that it needs to send or etc. So TCP and UDP are both valid protocols to use at the transport layer. Up here at the top, they show a couple examples of UDP applications, applications that would utilize UDP and applications that would use TCP. This graphic does a nice job of telling you the properties of the various protocols. These are the properties of UDP, and these are the properties of TCP. So this is a good graphic to just kind of solidify your understanding of what we've talked about thus far. So the next thing is how does a connection-oriented protocol actually work? TCP provides connection-oriented conversations by establishing sessions. It ensures reliable delivery and ordered data reconstruction. In other words, it puts the data back at the receiving end in the order that it was intended to be sent. And it also provides some provisions for flow control so that you don't overrun the receiving host with more data than it can handle. So once TCP establishes a session, it's able to keep track of that conversation within the session. How does it do that? Well, being that it's considered a stateful protocol, that it keeps track of the state of the communication session, it is able to manage that process very effectively. What we're showing here is actually what a TCP segment looks like. A couple of fields to note is the source port and destination port. This is how the TCP segment keeps track of the essentially the socket port, the IP socket port on each particular host, so that it knows that it's talking or to what it's supposed to be talking to. The sequence number and the acknowledged number come into play to kind of keep track of where it's at in terms of what segment this is that's sent, what's the last acknowledgement number I received, etc. So pay pay close attention to these definitions of these fields. These are tested on in the curriculum, so pay good mind to this. So as we said, UDP does not reconstruct data. It's connectionless. There's no flow control. It's unreliable delivery. So you know, it's pretty much put it out there and throw it against the wall and hope it sticks. The UDP datagram is still similar. It has a source port and a destination port, but notice it doesn't have any of the fields that control a session like the TCP datagram did. So what happens in TCP and UDP is it utilizes ports. Ports are kind of like a segmentation of an IP address. Based on the protocol stack, the IP protocol stack on a given host, it may or it is receiving or sending on different port numbers through that IP address. For example, the standard port number for electronic mail or email is 110, HTML is port 80, internet chat 531, and there's a whole list of different ones that are out there that get used. So again, with port addressing, here we see in the actual segment where the application port and the from a device is actually being mapped as the segments are being built on the particular application. So for example, the application port is for POP3, HTTP, and TCP. This graphic kind of shows how it actually ends up looking in a complete IP packet or a frame, where you have the destination source MAC address and the source IP. I guess this is an IP packet. I'm sorry. Shows the destination source MAC address, the source IP, the destination IP, the source port, and the destination port. So all this information here within the packet is what is keeping track of where it's supposed to go and how it's and exactly what port it's supposed to talk to. The ports themselves, there's what we call well-known ports, which are from 0 to 1023, and these are basically universally standard port numbers. There are also some registered ports that are registered for particular vendor applications, and then there's private or dynamic ports that can be user assigned. A lot of times you may want to use these to take a well-known port application or a registered port application and make it more secure by using a private or a dynamic port. So, for example, registered TCP ports would be like MSN Messenger, Cisco SCCP, whereas well-known ports are just the standard protocols that are pretty much universal. Registered ports, these are again some registered ports that are typical, and as well as some well-known UDP ports. So what the NetStat does, if you do this on your PC, it'll actually show you what ports are being used. These are the port numbers that are being used. the IP address, etc., whether it's the protocol is TCP or UDP. That shows you the destination port. So this is the source port. This is the destination port. It gives you the mnemonic for that particular port in the netstat. And then it tells you whether or not the state is established or not. So what the transport layer does is it divides the data into pieces or segments and then adds a header for delivery over the network. So UDP header provides for the source and destination ports. The TCP header provides for source and destination ports the sequencing of the particular segment so that it can be reordered properly. It also handles acknowledgement of received segments and also flow control and congestion management. Stuff we've already talked about. So there's some activities here on just reinforcing what you have learned so far. Then we get into flow control and this takes you through an explanation of flow control in TCP segments and how acknowledgements are used, etc. You need to take some time and go through that. There's a concept about window size, which is basically how many packets it sends at a time, or segments it sends at a time before it needs an acknowledgement. And the window size can have a lot to do with how much overhead your connection actually takes. Because if it has to send an acknowledgement for every segment, that could be a busy connection. So some stuff here on flow control and that sort of thing. This is something you'll be tested on in terms of being able to understand and how this all works and what segments need to be assigned, etc. So this is something you'll need to spend a little time on to get mastered. So with UDP, it's a lot more straightforward because it just basically doesn't care. This is pretty straightforward. So the other thing it does here is it starts talking to you about specific applications that use TCP and specific applications that use UDP. You're going to need to know based on an application which one it uses. You will have to understand that as far as the major applications that are out there. So on a test question, you may have a list of various applications and you'll need to choose, is it UDP or TCP? Activity 7244 does a real good job of priming you for that. So that's pretty much it for Chapter 7, the transport layer. You know, really work the activities on this. It is tested quite heavily in the final exam. It's especially in terms of knowing which applications belong to which transport layer protocol, as well as understanding how the things actually are acknowledged. Sorry about that. I got interrupted. But anyway, that pretty much wraps up Chapter 7. Your assignments for this week, let me check here and see what we got. Okay. Let's see, chapters, let's see, we're week 11, aren't we? Just got a one packet tracer, light week this week. But I would encourage you to go ahead and do anything and everything in that chapter it'll let you do, if for no other reason than to, boy, my computer's acting up. Really? Try that again. Okay, well, looks like my graphics on my computer is deciding to be a little fickle, so I'll just end it there. But again, go ahead and try to do everything that's available to you in Chapter 7 as far as activities, labs, packet tracers, etc. It's only going to make you better. Goodbye for now. Bye.